theta is going to be, the r is going to stay, right? It's sine, and is it negative or positive? Negative. Good way to remember once again is the graph of cosine in the beginning has a negative slope. Derivatives represent slope. Okay, good there. We need y. Partial of y with respect to r will give me sine theta, right? Partial of y with respect to theta will give me r cosine theta, right? Look good so far? Questions? Okay, so if we want to find the Jacobian, all we have to do is plug into the determinant, right? Okay, across the top I'll run with x, so cosine theta, my determinant's enormous, negative r sine theta. Now run it with y sine theta, and over here, r cosine theta. How did I know I was going to put with respect to r in the first column? We have polar coordinates. It's not like this, right? Polar coordinates have the first coordinate being r. Okay, so all we have to do is take the determinant of this jump. Determinant is going to be cosine theta, r cosine theta, minus sine theta times negative r sine theta. Oh, you figure out what it is. And then feel really good about yourself. Okay, I get r cosine squared theta, right? Plus r sine squared theta. What can I do with this? Back on r. What do I get out then? I get out r, right? What do we add in when we do conversions over? When we convert it over to rectangular, what are we putting on the inside? It's r, right? We put r on the inside. And this totally makes sense as to why now. The only thing you're blaming me about is the fact that it's because of the Jacobian. But would I lie to you? Probably not.
Does that make sense to add in the r if we're going from polar to rectangular? When we're doing the integrals, we're going from rectangular to polar. So, should we do the opposite?
But the cool thing is essentially what we're doing is we're writing x and y as functions of u and v. That is, we're writing x and y as functions of r and theta. And so essentially what we're doing here is, despite the fact that we're converting, when you think about your transformation here, you think about converting this way, essentially what we're doing is we're rewriting each of our functions as a function of that original, of the new variable, I guess. So when you think about what you're doing with your actual functions, you're using this, right? You're replacing x with this. You're replacing y with that. Okay. And so the transformation, the reason why this works is because when you replace that, when you use that substitution, the transformation is still mapping your points over. You got really excited there, and I don't know if I actually answered your question.
In my mind, it seems to me like we're going from x, from rectangular to polar versus...
From polar to rectangular. And I'm saying the reason why it works is because essentially what we're doing is by replacing this with this, we're using these functions instead, and the only way the integral will work is if these functions map back to our original. So when we replace it with integral, we're actually using that original transformation to make sure the integral still works. We're essentially using a substitution, and then the transformation is what allows us to do it. Okay.
Keep going. I'll keep thinking about this.
Okay.
That makes sense later. I'm good.
Okay, sounds good. So what we want to do is we want to look at an actual example. Not just calculating the Jacobian, not just looking at this. So, let's see here. Example we're going to look at. bound by the x-axis, y squared equals 4 minus 4x, y squared equals 4 plus 4x, and y is greater than or equal to 0. This, sorry, mine's on the board really quick, is the transformation we're going to do with it. Why did we start converting things over to forward world? Why did we ever do that? Use the circle, right? Because the shape that we had that we wanted to integrate over was inconvenient to do in rectangular. So we sought to do it in something easier. That's exactly how all transformations work. However, not all transformations are based off only a certain shape in the domain. Sometimes when we look at these, what we're actually concerned about is how hard it's going to be to integrate over geometry that looks like this. And so the first thing we're going to do here is we're going to try and visualize R a little bit. Let's see why this is happening. Okay, I know I want the x-axis to be bound. I know y should be greater than or equal to 0. Which means what? Where's my graph going to be? I know it's going to be above the x-axis, right? So I know I'm cutting it off and above. I need to visualize these things now. Y squared equals 4 minus 4x. Well, that's not really convenient. It's a parabola, right? Which way is it facing? Well, first, x or y-axis. Which way? It's going to face along the x-axis, right? Which means to visualize this, it would probably be best to isolate x. I want to isolate x really quick. Suddenly this should look really familiar. Look kind of familiar. Let's see here. If I move that 4 over, if I divide by negative 4, I'll get 1 minus 1/4 y squared equals x, and I know we've seen this today. You know what we're seeing this today? Okay, let's do the other one too, just to kind of visualize it. I've also got y squared equals 4 plus 4x. Which if I isolate over is going to give me 1/4 y squared minus 1 equals x. Okay, so far? Questions? No? Now, I know some of my bounds here. I know I've got these parabolas, but I also need to think about what other bounds do I have? That is, what information do the other two parts of this give me? What other bounds do I have? What other bounds do I know? I know the x-axis. How do I represent the x-axis? What equals 0 for the x-axis? Y equals 0, right? So I know we got a bound at y equals 0. So what I have to do now is kind of sketch these. Well, I can use the same strategy here. I know this is going to come out to x equals 1, right? And it's going to go up to 0, and it's facing this direction, so I'll take that. Yeah, here. I apologize if that sounded confusing. When x is 0, I'm going up where it hits the axis. That's this one right here, right? That's okay with that? And, sorry. That's this one right here. Okay, no. No. Which one is that? Plug in 1. Why is this hard right now, guys? This one. We're good. It's golden. I was totally right. There's some silence. You're scaring me. I'm full of fear right now. Okay. We got that second one?
It's okay, I think Marshall will figure it out.
What the point y equals 1 and x equals 0?
What?
Like, the point, 0 and 1. Well, I mean, why do you put it there?
Why do I stop right there? Because if I keep going, this is a good question. I could have kept going, but we knew from before these were going to intersect.
I mean, in y-axis, like, when x equals 0, where did it go? Because in the y-axis equals, y equals 1, right?
On the y-axis,
No, yeah. So how did you stop there?
how do I stop there?
Yeah, I mean, how would you collect this point?
Because we know what these look like. We did this example earlier, so I'm graphing them off what we knew before.
Oh, okay.
Yeah. You can plug in points if you want to get them.
Potentially, because,
Yeah.
okay.
The other way to think about it is I have a transformation of 1 up, and I'm facing negative. I have a transformation of 1 down, and I'm facing positive. And I've got my y-axis right here. So the question is, guys, we know that this is r, right? And what we can do is use r then to visualize s. That is the new region we're going to integrate over. Because our whole goal here is to do this transformation to make the integral easier on ourselves. Is that going to be especially easy to integrate over? That one right there. Why do we go? No, I mean, I could divide it like this, right? I could do that type 2. I have a left and a right curve, but then my bounds would be those, and those are going to be kind of awful to plug in and deal with, right? So what I'm doing is I'm transforming it over instead. What I need to do now is visualize S. Well, we already know what S looks like, right? Because we did this exact same example earlier. What is S if R looks like that? Square, right? If I square it. What were my bounds? I went from 0 to 1, right? And 0 to 1. Which means, now that I know my bounds in the UV plane, and once again we could use the same option we used from before, that is, if I wanted to, I could come over and use these transformations to try and solve out. All I need to do is set it up. What variable am I going to integrate with respect to first? Which one goes on the outside? I want you to look at the formula we wrote down. V, right? V was on the outside. That is, I had du dv, right? On the outside, I'm going to put the bounds for V first. What are my bounds for V? 0. What were my bounds for U? Which means that, what else do I have to find here? Well, I need to find what y is equal to, because that's what was originally in the center, right? What is y equal to in this case? Y is 2uv. What else do I need in there? I need my Jacobian, right? So, let's find the Jacobian. I want you guys to try finding it on your own.